Just want to make sure I have the chat window and everything pulled up. By the way, while we give it a couple more minutes here, I've already gotten several direct messages through Discord. So if any of you guys that haven't messaged me yet are interested in getting some help, whether or not it's composites related, right? It might be structural optimization, it might be CFD, electromagnetics, motor design, anything, shoot me a message and I can see how I can help. If you attended Eric's session earlier today, you probably are familiar with Altair, but I myself am also a solar car addict, so I'll do whatever I can in and outside of Altair to help you guys out. All right, well, I suppose since we're being recorded, we might as well go ahead and get started. No worries if we're a little bit late here. First off, I'll introduce myself and Altair. If you're not familiar with Altair, we are a growing simulation company founded back in 1985. Originally, we're a consulting firm focused mostly in the automotive and medical industries. And since we've grown with a software suite, but we still have a large portion of our business coming from consulting. And that's actually where I spend most of my time. So my specialty is in composites design and optimization. I do have some background in CFD, so I can help you guys out with that. But anything outside of structural FEM and CFD, I'd be happy to point you guys to the correct resource within Altair. Let me go ahead and share my screen here as well. I can find there it is. All right. So I know I've only been allotted 1 hour here, so I'm going to move pretty quick with the understanding that it is recorded, so you guys can go back and stop and pause. I'm going to try to stop a few minutes early for Q&A, but with that being said, feel free to shoot a message in the chat or just interrupt me if you'd like, if you want to stop and talk about something in a little bit more detail. All right. All right. So accurate and efficient simulation of laminated composites. If you guys haven't worked with composites before, it is very different than working with isotropic materials such as metals and the like. But I found that the solar car community definitely has a great need for composite simulations. I know when I was on the team a few years back, I did most of my composites calculations on the back of a napkin. Didn't really model a whole lot. We kind of over-designed and overbuilt everything, and it was a very robust car, right? We knew it wouldn't fail, but it certainly could be significantly lighter. And so this is a topic I felt could be valuable to all of you guys and share with all the crews. So I'm going to start by just giving a brief intro into composites for anyone that might be new, freshman, sophomore. If you guys are just kind of getting introduced to this world, It's a pretty cool world. It's riveting. A lot of breakthrough technologies coming out of it. I'm going to demo a model build of a composites model, go through an analysis and post-processing of it. I'm not going to have time in my allotted hour here to demo a full optimization problem with composites, but I will kind of walk you guys through what that process looks like. And if you're interested in seeing more, again, feel free to direct message me and we can schedule some time to do that with you guys one-on-one. I also want to go through some fidelity concerns that people have. I know most places around industry, they do require, and I think even in the BDR, you guys have to submit. It is required that you submit your composites models using solid elements, aka hexas or tetra elements. That is no longer, that's old news. The aerospace industry is very slow to adopt it, but there are other industries that are already advancing in that you no longer you do need to model with solid elements, right? We have this technology where we can model materials within a unit cell, apply that to a shell element or a 2D element, if you're not familiar with the terminology, and still not lose any fidelity. And so I'm going to talk a little bit about that, and hopefully we'll have some time for Q&A. A little bit about me. Again, I graduated in 2019 from University of Minnesota. Spent several years there racing. Participated in 4 races here between 2015 and 2018. Was very involved. Spent my time as the aerodynamics and composites lead while I was there, and I've been hooked ever since. So now within Altair, I focus on structural FEA and of course composite design and optimization. And also, I'll make a note here before I move on that if anyone is looking for internships next summer, also feel free to send me a message. We are actively hiring. All right. So what is a composite material? Most of you are probably familiar with this one already, but a composite is any material that has merged 2 individual materials together to create new material characteristics, new material properties. And these come in a variety of different types and forms, one being particulate composites. We got laminated composites, fiber matrix laminated composites, and of course our core stiffened laminated composites. The model I'm going to show you guys today will focus on that third one there, fiber matrix. I know most of your parts do have core in them, and I'll talk about that briefly as well if you want to include that in your analysis. But the full-blown model I have here will just focus on fiber matrix. Advantages to composite design, of course, we can engineer our own properties, our own application requirements, right? That's the big thing. We can import required properties there. So this is not something you can do with homogeneous materials like steel or aluminum, any metal of that sort. Now that is changing with the new technology of friction stir welding, using metals to create very difficult parts is now, there's a lot more freedom in that industry now. I don't know a whole lot of the details, but that's a growing technology as well. But composites also have an increased strength to weight ratio, right? They're very light compared to metals there. So this is one example here I wanted to share. We've got a simple square steel plate. It's in tension here. And the requirement is that we don't want a displacement of more than 0.1 in the X direction, right? And so in metals, obviously this is very easy to do. We would just make this plate thick enough so that it doesn't displace 0.1. It's going to displace the same in X as it is in Y. Obviously, the requirement down here is that Y can be no more than 0.025. With metals, that makes it very difficult if we're just looking at a steel plate, right? That would require us to change the geometry, change the shape of the part. We'd have to vary the thickness in some way to accomplish that. But with composites, we can simply add in additional plies in that Y direction, right? Holding the displacement in that y direction to the 0.025 that we needed, and allowing the x to get out to that 0.1. And so there's a lot more flexibility and opportunity there to use composites to your advantage without changing the shape or geometry of your part. Here are the requirements that you need whenever you're modeling a finite element model for metals or composites comparatively. Of course, in both of them, you're going to need your geometry and material properties. In metals, you also need your loads and boundary conditions, your visualization of the results, and then you're going to want to model your failure based on invariance only. On the composite side, of course, you need a lot more. You need to assign your ply orientations, you need to define your constituent properties, and this is something I'll talk a little bit about when I get to that fidelity issue, right? Where we can model the individual fiber and matrix constituent properties to figure out, okay, my part failed. Did the fiber fail or did the matrix fail? And that can help us determine which one of the two needs to be improved in our design. Of course, we still need our loads and boundary conditions, visualizing the results, and then our failure is also going to be based on 3D stress state, directional, and it's dependent on our constituent properties, right? So we're not only concerned about those invariants as in metals, a bit more complex. But because of that there and our ply orientation requirements, this is something we need to be very aware of when building a composite model, and that is the element coordinate system. So if you're familiar with FEM, and it's okay if you're not, each element is assigned to these G coordinates, right? G1 through 4. And your X by default is always that G1 to G2 edge of your element. Your element coordinate system is, of course, different from your material coordinate system. Your material coordinate system is defined by a theta off of G1, G2. So if you're looking at a 45-degree ply, your material direction is in 45 degrees of that element. So obviously, you can't model a composite that has one element with 45 degrees here, and the other element you might assign 45 degrees, but because G1, G2 is in a different direction, it looks something like this, and that's physically impossible to do on a manufacturing floor. So it's important that we get all of our elements properly oriented so that we can build our model with the proper orientation. Strain stress relationship is very different as well. So right now I'm basically just listing off all the differences, the things we need to consider on top of what you'd normally consider in an isotropic case. But here, using isotropic linear elastic materials, we've got this simple matrix here, which is given by this equation here at the bottom. I don't know if you can see my mouse on the screen or not. But when we look at composite materials, that equation gets a little bit more complicated. So it's rewritten like you see here. So if you look at this image up top, you can imagine if we're pulling this in tension in the one direction, it's probably a lot stronger than if we were to be putting this in tension in the two direction, in that y direction. And that's because that would require entirely, or that would be dependent on the strength of your matrix there. So a lot of things to consider. And I've seen, when I was in your shoes, I've seen a lot of teams do their layups without considering the orientation of their plies at all. And no matter how thick you make your part, that's a little bit scary to think about. Because if all of your plies are in the same orientation, it could just, be one accident and everything falls apart. It's very important to consider all that. Okay, getting into the specifics of composites modeling. And again, I know I'm speaking fast. Feel free to let me know if there's questions. Otherwise, hopefully I have some time at the end. So zone-based data. This is how composites modeling got its start. So back when composites modeling became a thing, we were defining our plies using zones. So I think if I go to the third slide here, this makes it a little bit more clear. We have zone 1, which is this red red piece here, zone 2, which is this blue piece, and that's just our ply shape. So this is saying that ply 2 here is only covering this end of my channel there. If I add another ply that covers the inseam of both of those, I'm looking at 4 zones, right? Because zone 1 and zone 2 have different thicknesses, potentially. So when I add a third ply there, I've now got a different thickness in each of these areas. So now I'm having 4 zones and only 3 plies. This can get a little bit complicated, right? So actually, if I can, let me see if I can open up the paint tool. Awesome. So how do I explain this? So if you imagine, let's say I have ply here, I've got another ply here, and I've got another ply that does something like this. And then we'll just give it one more over the top. Obviously, this is giving us 2 zones, right? Over here, we've got ply 1, 2, 3, and 4. Sorry, that's a little sloppy. Over here, we just have 1, 2, and 3, right? But you probably noticed that my ply ID of 3 over here doesn't match my ply ID of 4 over here. And this was the inherent problem with zone-based modeling, because if you wanted to quickly change your laminate and you deleted ply 3, you're not deleting ply 4 over here, and now everything is messed up. So then came along something called the PCompG, which is a global zone-based modeling or global IDs. And essentially, that got rid of this difference in naming convention, and we were left with 1, 3, 4 over here, right? So now I still only have 3 plies in this zone, but it still recognizes the same ID across. And this is PCompG. It's still widely used in industry. In fact, a lot of people will choose to build their models with ply-based modeling, which I'll get into, and then convert it back to zone-based to solve in, in other solver like ANSYS, Nastran, Dyna, etc. But if you're solving an Optistruct, which is what I'm going to do, there's a much cleaner way, which is called ply-based modeling. And that actually doesn't require us to even define a zone here. So you can eliminate that there. And we're just going to define the plies as they are. So when you build a ply-based model, you're building it as you would on a manufacturing floor. You're defining 1 ply at a time and stacking them in sequence. And you'll see that here as we move forward. I see there's a question here. Is it a good idea to use isotropic properties if using a quasi-static layup instead of getting material properties for orthotropic plies from physical testing? That's a good question. I personally would say no, simply because of the lack of concern for constituent properties in that case. You could, as a baseline, if you're just doing some baseline tests at the start of your design, you could certainly assume isotropic properties for some laminates there. But even in a quasi-static layup like that, I would venture against it for sure on your final report. But it's a good idea to speed up your initial baselines for sure. I know I've done that plenty. So here's ply-based modeling. We're essentially going to define all of these as single plies, right? You don't see any broken up zones here. And if you're to zoom in here where those 2 zones were separated in the first example there, all you're seeing is a ply drop, right? So we've got these 2 extra plies over here in this zone that are not present over here. Now this ply drop that you see here, this void, is nothing to worry about in your mesh, because what you're seeing here is simply a 3D visualization of 2D elements. It's a little bit misleading here, but these are not 3Ds. We're basically modeling everything with 1 2D sheet and then assigning plies or layers on top of those elements. So I'm going to skip through these. Yeah, I'll quickly show this here. Typical modeling workflow. We're going to define our stacking direction, right? Very important. That's dependent on your element normals. So that'll be your stacking direction. Of course, I mentioned we want to define our material orientation. We'll create our plies, defining our thickness, material, our shape, right? Which would be those zone 1, zone 2. We'll define all of those plies into a laminate. We'll create our template, solver specific attributes. For Optistruct specifically, we'd use this pcomp-p. If you're using Dyna, for example, you might use pcomp-g, but there's other terminology out there. And then, of course, draping simulation is very important at the end as well, right? Because especially on a curved piece like this, if I were to drape a piece of carbon over the top of this here, the orientation that I'm laying my carbon is not necessarily the orientation that it will end up in, right? Because it stretches around those curves. Your fibers will change direction ever so slightly. And of course, you're not going to be cutting out a simple rectangle here, right? Your shape is going to look something like this. And so doing a draping simulation will give you a lot of information, so you're not wasting too much dry material before your wet layup. All right. So yeah, back to orientations. This is just off of that draping thing that I just mentioned, right? Obviously, every element has its direction G1 to G2. That's your element centroid. Then you got your reference orientation, which is by default always going to be your 0-degree fiber orientation. Your fiber direction then is going to be your ply, right? So if you have a 0-degree ply, this theta here, theta k, will be 0. So that's going to be the same here as same as this one here. But if your nominal fiber orientation is 45, then this theta here will be 45. Then of course you got an extra theta change there based on your drape. So let me jump out of this now and open up the tool here. So I've got that same model here that I showed in those slides that I figured would be a quick demo here to show you guys. And I know I'm already almost halfway through here, so I'm going to move fast. But as we talked, one of the things I mentioned was the first step in any model definition here is my element normals. If you're not familiar with FEM, don't worry about the mesh here or how I got the mesh. If you guys want sort of a quick dry run or short course on meshing techniques and how to properly mesh models for different types of analyses, right? Because your meshing is very different for CFD as it is for a structural model. Again, feel free to direct message me. I'm happy to talk to you guys about any of this stuff. You know, whether or not you mesh in HyperWorks or ANSYS or you know, any of those tools out there, I'm happy to take a look at your models. But here, if I zoom in, you'll notice that in this model here, we just have some 2D elements, right? No 3D hexes, no tetras, nothing like that in this model yet. All I've got is the surface and some 2D elements there. First thing I want to do is check my element normals. And again, I'm not going to treat this as a training per se, so I'm going to move kind of quickly through the button clicks here. We can always give you guys some training later on if you reach out, but I'm just going to kind of demo what we're doing here. So I'm going to view my element normals here. You can see that I've got this red and blue. Red is the positive direction of my vector. Here I can try to change this here, make it a little bit more clear. So if I zoom in here, you see my positive direction is pointing outwards there. I'm just going to go ahead and reverse that. I'm going to treat this as the inside of my mold, and I'm going to lay my plies on the inside of the space here. So I want my direction facing inward, like you see there. All right. Next thing I want to do is open up Composites browser here. And I'm going to create a material reference orientation, right? And this is to make sure that all my elements are facing the same direction. So let's select all my elements to start here. All right, so I'm just hitting review to start. this is what my elements look like from the get-go, right? And this is the default, and the default is using my system axis here. So I could assign everything to my system ID, which would just be selecting that there. And I can put in custom or local rosettes, right? Local coordinate systems anywhere I want in my model to change my orientation there. So if I hit apply, you'll see that doesn't change, right? Because this rosette is set to the same orientation as my global axis here for the most part, at least in the X and Z there, or the Y and Z, I mean. Now, if I change, let's do this. All right, I'm going to change this to curve, and I'm going to select my lines as I'm going to change a setting in here that I don't necessarily like. All right, let's try that again. There we go. Select my two lines, and let's hit apply. Now, if I zoom in here, you'll see that all my orientations follow that curvature, right? There's no bending up here because of the bend of this piece. I'm actually going to flip the direction though, so everything's facing over in this direction still. So now it's following that curvature. That's what I want. I'll go ahead and hit apply, close that, and my material orientation is set. So that's going to be my default 0 direction. The next thing I need to do is start creating my shapes, right? And I'll do the exact same thing as we saw in those slides to show you how that's done. I'm gonna go ahead and just create a shape here. We'll call this one the full shape. I'm just gonna select all of my elements, right? That's my entire model, entire build there. And I'll create a second one here and we'll call it partial. And this is just gonna be this piece over here. All right, I think I got it all there. Hit OK. So now I've got my two shapes there. So now I'm going to use those shapes to go ahead and create some plies. So ply 1 here, we'll leave my orientation at 45 degrees. We'll give it a thickness of say 0.2. I'm going to assign my material here as carbon epoxy. And that material I already had predefined here to save time. But essentially what I've done is I've created two materials, carbon and fiberglass, and I've defined their properties down here. Both Mat 8 cards you see here, that's telling me that I need orthotropic properties assigned to both of those, right? So those are defined. One thing I'll mention on this too is, and this is a little bit different from what you probably saw earlier in Eric's presentation, in that HyperWorks here, being that it's a different interface, is completely unitless. So any model you bring in from CAD, if you're using the metric system, for example, or imperial system, it's going to come in that system, right? So all of your dimensions, all of your material properties need to remain consistent within that measurement system. But if you want to change it, it's up to you to go in and modify these values accordingly. The default is always going to be steel. If it's blank and then populates a default number, that's the steel value of that number. But again, it's unitless. It's up to you to make sure that everything is consistent, right? It's not going to error out if you've put E1 with the imperial units and E2 with metric units. It doesn't know the difference. So It's up to you to make sure everything's consistent. So we'll leave that as carbon epoxy, and then my shape here, I'm going to set my shape to be that full shape, right? So this is all of my elements. You'll see it outlined there. So I've created my ply one, right? And as you're using ply-based modeling here, the idea you can keep in your mind is visualize how you're building this on a manufacturing floor. As you stack each ply, you want to define each ply as you're laying it down, right? So now what I'm going to do is I'm just going to right click on ply one here. I'm going to say duplicate. I'm going to say duplicate that 7 times. That'll give me a total of 8 plies. And now what I can do is just come in here and modify these a little bit. We'll just update everything so that it gives us a clean build here. And I'm also going to change the color of all these so it's easy to reference. You'll see as I click through these, you can see the different shapes that are assigned, right? So if I take ply 4 and 5, actually let's take ply 3 and ply 6, and yeah, those are good. And then we'll assign this shape here, right? So now if I highlight this one, it's just giving me that shape there. And those are going to be kind of squeezed inside of my laminate there, like so. And why I chose 3 and 6, completely arbitrary, no reason whatsoever. So I've got my 8 plies. Next thing I need to do is then assign all of those plies to a laminate. I'm going to go ahead and create a laminate 1, and I'm just going to drag these up into that laminate there. I'm also going to make it symmetric, right? Well, let me hold off on that for now. Show you guys what this looks like. So I've got my laminate built. One more thing I need to do is define a property, and this is for the solver that you're going to be running it on. So if it's Optistruct, you want to use the pcomp-p. pcomp-g, pcomp, and pcomp-ls are all available as well. LS is what you're going to use if you are modeling with solid core material. So typically for these competitions and the teams I talk to, if you're going to be modeling with the core material, you want that core to be modeled as a solid element, and then your shell elements will be around it. So your pcomp LS will be defined or assigned to your core, and your pcomp P will be assigned to your actual plies. And I'm gonna kind of skip over that for now, just because I don't know how much time that would take to go into detail on. I'm gonna assign this pcomp P, and then this is just gonna be my Z offset. So I'm gonna set that to 0. Again, to be clear about what I'm doing there. If this is my surface that I've meshed, by default, when I assign my laminate to those elements, half of them are going to be on this side and half of them are going to be on this side. So this is the midplane of my composite, right? If I set Z0 equal to 0, it's telling me stack from the 0 points of my elements in the element normal direction. So if my element normal is facing up, it's going to start here at Z equals 0 and stack up, ply 1, 2, 3, and so on in that direction. If I had Z equals minus my T over 2, so minus half of the thickness, then of course it would start down here, and that's the default. It's a lot of different options you have there. And this becomes important if you're dealing with interface laminates, right? So if, for example, an I-beam, right? How would you model this with composites? The element normal here might be going in this direction. Here it might be going in this direction, right? So what happens when you have a ply that wraps around these two here? These elements are now being stacked, or these plies are being stacked in a different direction than these elements here, right? So then that's when we use something called interface laminates, and we can readjust these parameters here. Again, I'm not going to go into that much detail on this model. We'll keep it very, very simple here. So Z0, that's what we want there. And that should be all we need just to visualize it. So now what I can do is change this to property view, and I can show you guys what this now looks like. Did I assign? Oh, hold on. I need to assign my property to my component here. It's easy to forget the little things. All right, so here's my laminate that I just created, right? Obviously, remember plies 3 and plies 3 and 6 are the two plies that I only assigned to the partial side here. So this here is the ply drop, right? So I've got a thinner laminate over here than I do over here. If I go over here again, you can see the plies a little bit more clearly on that end. So now, if I, for example, change my laminate to be symmetric, you can see that thickness just doubled, right? I've just made my laminate symmetric around Z equals 0. So I've got those voids on the top and the bottom there, my center plane. But again, remember, this is only a visualization, right? So if I turn off these features here, I'm still looking at shell elements. All of my boundary conditions, my constraints, my loads, everything is assigned to these elements here. I don't have to worry about assigning everything to those 3D spaces over here on the side. Those are just for visualization purposes. All right, so my model is defined. Before I run my analysis, let me just skip a step here and show you guys a couple other things that's in this interface before I leave. And that would be one being the draping. So let me show that first. If I right click on laminate here, excuse me, and go to drape, this is where I can define my ply shapes, my drape angles, right? So what I'm going to do here is actually turn off these first. Go back to drape. I'm going to select my seed point. So this is just the point where your ply is going to touch the part first, where it's going to touch the mold first. So we'll say I lay it down right there. I'll hit apply. And this will give me all those flat patterns that you guys really need for your manufacturing. So right now it's going through all 16 plies that I have in my model there. All right. So for example, go to ply 3. Let's review the drape mesh. That's what my draping is going to look like. You can see the orientation changes ever so slightly. If I go to the shear, right, this is going to give me the shear pattern on that particular ply. And I can also take a look at the flat pattern. So that's the actual shape that I want to cut out. And because I believe was ply 3 was in the 0 orientation. No, so this makes sense. I'm cutting it in this shape, and this here is pointing in the fiber direction. So I want my fibers in that 0 orientation that I defined previously. If I go to ply, let's go to 90. So ply 4, right? Now you're seeing my orientation is in the 90 and my ply shape here. And of course, I can export these as DXF files. So you can use them to trace and cut your plies in the clean room when you're building your part. So it makes it very quick, very easy, and you're no longer wasting so much dry material in your labs. I know that's hard to come by on those student teams, relying on sponsors and all. Let's see what else. I want to show the stress toolbox here. So this is not new, but it's something we've changed recently to make it more accessible. Um, and what I can do is go into my laminate here, I'm going to analyze engineering constants. And this allows me to take a look at all of my matrices for that laminate in both zone 1 and zone 2, right? So this is for zone 1, I've got 12 plies. I've got my ABD matrices here. I can change this to a plot, right? So I can take a look at my stiffness in the fiber orientation, my stiffness in the matrix direction, and understand that, okay, my 0-degree plies were over on this piece here. So for zone 1, my strength in EX should be actually very low in the 0 orientation, right? Because all my 0 plies are in this shape here. But it should be strong in 0 for zone 2. So let me actually look at a ply here. If I open up ply 3 and do that same thing. Yeah, so again, we got our out of plane constants, our 2D and 3D matrices there, our homogeneous matrices. Let me look at EX. So yeah, for that particular ply, of course, we're strongest in the 0 direction. In EY, we're going to be weakest in 0. We're maxing at 90. So that's exactly what we'd expect for that particular ply. So this will tell us, if we're looking at it at the laminate level, in which direction are we weak, right? We'll figure out our weak point and make sure that we're not going to experience any loads in that direction, whether it's tension, compression, or whatnot. And all of these results are given for both tension and compression if you're building them with the material modeler that's in-house here, which I'll show briefly here in a bit. I'm trying to think if there's anything else I wanted to show before I move on here. One thing, I know a lot of you guys don't solve your solutions with Optistruct. If that's the case, I don't want to be biased. So if you wanted to build your model like this and then solve it in, say, ANSYS, Dyna, Nastran, whatever you have, what I would do is build your model just like I did here. Then I'm going to right click on my laminate here and I'm going to say realize. This is going to change it back to that zone-based definition that I talked about, that pcomp G, and that property, that solver deck, can be imported into ANSYS, for example, or Dyna, and you can use that to then solve the model there. Otherwise, you can just, if you're in HyperWorks, you might as well use Optistruct. It's right there for you. But completely up to you guys. So with that being said, let me actually go ahead and run this quick. Let me show you the loads that are assigned to it so that you know what's happening here. Right, so over here on the right-hand side, right, I've got all my constraints, right? I'm constraining that end, and I am loading this end in compression, right? So all of these nodes here have a loading that is pointing in the inward direction. So if I, hold on a second. Yep. Yeah, it's all pointing inward. So this is in compression. Just wanted to make sure I wasn't going crazy there. So that's the setup I have here. Another thing I want to do before I run this is make sure I request the proper output for a composite solution. So I want my composite strain and my composite stress, both in H3D formats. Here it's going to ask for type, and it's also going to ask you for number of divisions. This is for each individual ply. So I can take a look at my results on each ply 1, ply 2, ply 3. And if I increase this value here to say 2 or 3, that's how many times it's dividing that individual ply up, right? So we can get the peak stress or the peak strain at the top of my ply and at the bottom of my ply, which becomes very important if you're really focusing on the constituents. For your case on these cars, I would just leave that at 1. But with that being said, we'll just go ahead and run it here. I'm going to go ahead and put this in here. Let me create a new folder called IEF, and we'll call this, let's give it a 22. And this should run fairly quickly here in a matter of 10-20 seconds. You can take a look at those results here. I don't know what happened to it. Oh, there it is. It's hiding on my other monitor. All right, so that ran pretty quickly. It's already done. We can take a look at our output file quick. Gives you some model information here, number of elements, etc. Okay, so this is what I want. Here's my volume, mass. There's my stiffness information. All right, let's go ahead and open that up again, and I'm going to open a new page here in my session, and we'll pull those results in to take a look at how our piece did there under loading. Again, we only had the one sub case here, so that's the only thing we need to worry about. We'll take a look at our composite, excuse me, composite strain. Simple, and let's turn on our mesh again. So we can see where our strain is happening here. So this is obviously our peak strain. I can take a look at this for individual plies. So maybe we'll go to ply 5 here, see what that looks like. And I can jump between every single ply in my laminate here and take a look at the stresses and strains on each individual one. Maybe I want to take a look at the total displacement for the entire laminate. I can animate that. Maybe we'll scale that up so you can actually see what it's doing there. Right, so remember it's constrained on this end over here and it's in compression over here. So it is behaving how we'd expect. So we've got our sanity check there. But I can go through and modify this. Maybe one thing I can do here, create another window, and let's jump back to my model here. And I'm going to change, let's get rid of this symmetric definition here, right? So now, again, we've only got the 8 plies now. If I zoom in here, you'll see I've only got the 8 plies now. There's 6 on this side. There should be 8 over here on the other end. Yep. So now we'll go ahead and run that one. as it is. I'll just say 8 plies. And there it is. So again, should run pretty quick. Go ahead and close that. Open up our post processor again. All right. And we'll compare our displacements. Peak displacement over here was 2.6. Over here, we're looking at 0.7. So obviously by taking away those extra 8 plies, we got a much weaker part. So we can go ahead and compare those side by side like that. So very good comparison. Nice tool to utilize to make sure you're understanding your results and defining everything appropriately. Since we've got about 10 minutes left here, I want to just quickly breeze through these other topics here, talking about fidelity that I promised. And then we'll get into some Q&A. All right. So this is something not necessarily new, but it is something that is just starting to take hold in industry. So I'll say if you guys can learn the concept of multi-scale technology, if you can learn the concept of multi-scale modeling, it's going to put you in the front of the line when it comes to pursuing a career in composites, because this is the technology that every industry wants right now, and is just learning about. So essentially what we're going to be doing is modeling even core. Everything we need to model can be modeled with shell elements, no longer a need for solids. And what we're going to do is create a single unit cell, a material model that we're going to plug in. Instead of our MAT 8 card, we'll create a MAT MDS card and plug that material model into our model to give our 2D elements a definition of a 3D unit cell that is in itself modeled with 3D tetras or hexas. So we're not losing any fidelity. We just got it pulling information from another tool, from another material database. And this can be used for unidirectional, continuous products, as well as discontinuous products like injection molding. So a very widespread. And this is the general idea that you should understand here. And that is that everything comes in a scale here. So let me jump to this slide first. This is a typical example of a metal, right? You probably heard the term of black aluminum, right? Black aluminum is this idea that even when we're dealing with composites, we can treat the entire laminate as a homogeneous part, as an isotropic part, we just assume that this is one material model. We average everything through the plies and we just do our analysis on the laminate. That is not okay anymore. That's how things used to be done, and that's how metals are done. So we were under the assumption that that's okay. The understanding here is that obviously scale 1 is the average of all of our of all the stresses and strains on the scale below it, right? So in the metals case here, we've got our grains and boundaries averaged all together gives us scale 1, or the ply level in metals, right? In a composites case, scale 1 is not the ply level. Scale 1 is fibers and matrix. That's our individual constituents. So up till today, we've been modeling everything at the laminate level, even the ply level in some cases now, but we're still building our boundary conditions and solving our models at the ply level. and we're neglecting this scale that's between our matrix and fiber and our ply, right? So we're solving metals at scale 1. Why are we solving composites at scale 2? That's the big question, and that's why people aren't getting accurate results in composite simulation. And so this is where you want to model on your fiber and matrix. Make sure you're pulling those results out the way they should be. And that's this idea of multi-scale modeling and why you should plug that into your shell elements instead of modeling with 3D. I'm not saying there's anything wrong with 3D solid modeling. Certainly you can go about that, but it takes a lot longer to solve your model, right? Your runtime is significantly increased. It's a little bit more complex. It's not as forgiving, especially when you're hex meshing. Your surfaces have to be aligned with each other. It's so much easier to model with shells and then just assign a material model. So this is a much preferred route. And then of course, the dehomogenization phase, right? So we'd still model our part at the ply level, we'd solve it, and then we dehomogenize it into matrix and fiber, and that's why we get those differing results. So it's a process, and I'd be happy to talk to you guys more about it if you wanted to later. And then real quick here, before I wrap it up, composite design optimization with Optistruct is very similar to what Eric showed earlier today with lightweighting. We're still going to use the concept of topology optimization as a first step. So we're going to take our design space here, we're going to constrain it, we'll apply a load. We're going to give it a total design space that is maximizing the bounding volume that our part can take up in the assembly in our vehicle model. We're going to run a topology optimization on that, and that's going to figure out the most efficient part shape, the most efficient ply shape. If you're familiar with topology optimization, you know that what it's doing is optimizing the density that's assigned to each individual element. If that density is 0, it's saying remove that element. We don't need it. And that's how it removes the material. If that density is 80% or higher, that element is critical to the load path. So we want to keep that element. So first and foremost, we're giving it a ply shape. Next, we're running a free size or size optimization, and that optimizes the thickness of each of those remaining elements. And that tells us how many of each of those plies we need. And finally, we know our ply shapes. We know how many we need of each of them. The last step is to optimize the stacking sequence. And that's called the shuffling optimization. We're experimenting with different approaches of that now as well. But shuffling optimization is the current approach that's recommended. And then finally, you always want to run a baseline, of course, before you review your results. Make sure everything makes sense. Do the eye check before you take these results for granted. I know Eric talked about this a little bit earlier today, but again, this is not meant to design the part for you. It's meant to tell you where the load paths are and help you understand the design, the shape a little bit better, so that you, the engineer, can make the important decision on what to do with that and where to place your material and with what orientation. So this is just a general workflow here. You've got your ply shapes, your ply thickness. Eventually it'll build into a nice model like so, right? And then you'd use this to interpret your ply shapes and cut them out accordingly. So I think that's all I had, unless there's something else I forgot, but here's my email. I've also pasted it into the Altair channel on Discord. If you're gonna want to reach out to me directly. This link here has some other solar car success stories from previous teams we worked with. And then if you guys are looking for a sponsorship, that last link there will give you the sponsorship information. So let me see if this works. So there's the link to our sponsorship app. Actually, I didn't send that to everybody. There we go. That's the link to our sponsorship application. So if you apply there for an Altair sponsorship, You'll get put in touch with Shannon, who's our inside rep, and she'll likely put you in touch with me or Eric or someone else who might be closer to you. But you're always welcome to reach out to me, and we can get you guys started. I see there's a couple extra questions here. Is it possible to look at any residual stresses in the laminate if it is not symmetric without any load cases, or we have to compare two different laminates to see the difference in the residual? Well, without any load cases, I don't believe that's possible to do as you stated it here. You do need some sort of load case, whether it be modal or thermal or anything. There's got to be some sort of load that will give it strain. Otherwise, you're not going to get any residual stresses. So I would say no to that question. Yeah, if there's any other questions, I'm in no hurry. I can stay on for a few more minutes if anyone has any. Otherwise, like I said, shoot me a message, and I'm happy to help. And again, like I said, if your questions don't relate to composites, that's all right. If you guys have questions on CFD setup or anything else of that nature too, I'm happy to help. Send them my way. With that, again, I'll stay on a few minutes. Otherwise, you guys have a good rest of your night, and good luck with your solar cars this year.